Okay, last class we were discussing the first derivative test and how we can use the derivative to determine local maximums and local minimums, right? We did an example, a couple of examples. We're going to do more of that today, but we're now going to talk about the second derivative test. Oh, I did send out the review, right, for the exam that's going to take place. We decided to just keep it on next Thursday, week from today. My plan is to do it kind of like we did last time. We take the test. After the test, we come back, we do another half class of lecture, all right? So we'll do it at the beginning, and if you finish early, you wait, and then you come back. All right, so the review I gave you had solutions, right?
Yes.
Okay, so see how that goes for you. We're now going to talk about the second derivative test, but let's just do a quick recap, real quick recap of what the first derivative test told us. The first derivative test says that if you're given a function, first derivative test says that if you're given some function, right, given f, and let's not even think about the domain right now, just if we're given some function f, then we can find the critical numbers. I'll put Cn for critical numbers, right? And we know how to find critical numbers, right? You take the derivative, set it equal to 0, figure out where it doesn't exist, right? Once we find the critical numbers, we plot the critical numbers on a number line. Something like this. You know, we plot these, it depends how many we have. We might have one, might have two, might have none, might have five. We plot them, whatever they are, right? And that will break up our number line into regions, and then we pick test points somewhere in between, or somewhere in these regions. We test those points, whatever they are, we plug them into the derivative to figure out if the derivative is positive or negative. And if the derivative is positive, what does that tell us about the function? It's going up. And if the derivative is negative, it's going down, right? So that will help us in these regions to determine if a function goes up, down, maybe it goes down again. But from that, we should be able to determine, first of all, where a function goes up and down, but then also any local maxes and local mins, all right? So let's just run through it real quick one more time. Given a function, find the critical numbers, which means figure out whether the derivative is 0 and doesn't exist. Plot those on a number line. Pick test points, plug those test points into what? The derivative, and then if the derivative is positive, the function is going up, derivative is negative, going down. Yeah?
Yeah.
Okay. Now, the second derivative test is the exact same thing that we just did, except we're going to be working with the second derivative instead of the first derivative, and it doesn't tell us, the second derivative test does not tell us about where a function is going up and down. It tells us something else about the function, which is what we're about to now talk about, all right? So the good news is that the second derivative test is going to be very similar to what we just did with the first derivative test, but we will be analyzing the second derivative. The difference is the conclusion is not where a function goes up and down, it's where a function does what? Well, let's talk about it. So here we go. Make this a little bit bigger. I'm going to show you this graphically first. So I'm going to move across this graph, and you're going to notice when I move across that graph that I have some regions on the graph that are red and that are green, right? Going off of last class, right? Last class, we were talking about where a function goes up, increases, and then where it decreases. Do y'all see that this green and red does not represent that? Y'all see where it's red here is actually increasing and it actually decreases as well? And then in this green, what there it looks like it's decreasing, right? But then so is the red, it's decreasing as well. And then this green, it decreases and increases. So what I'm trying to get you to see here is that red and green is not connected at all to the up and down of this function. Has nothing to do with it, all right? What it has to do with is something called concavity, the concavity of the function. So when you think about concavity, or when you're learning about this idea of concavity, the simplest way to think about it is thinking about a smile versus a frown. Smile, frown, okay? Look at the smile, right? A smile, right, is what we call concave up. Any graph that has a shape of a smile, or any part of a graph that has the shape of the smile, is called concave up. So look at the green parts of this graph. Do y'all see that the green parts look like part of a smile? Right? Like from here to here would be part of a smile. And then also from here, curving around and up, that would be part of a smile. I'm not saying it's the entire smile, but it's at least part of it, yes? And then the red part is part of a frown. This is part of a frown, right? And that's part of a frown. Y'all see that? The second derivative tells you whether or not your graph is smiling or frowning. Now, that's not the mathematical words for it. We say if the derivative is positive, we will say that it is if the second derivative is positive, we will say that it is concave up. Second derivative is negative, we say it's concave down. Do you have a question?
Yeah. Why is it green?
It looks, that's my, I was sliding my tangent line across.
Okay.
So, sorry, that's my tangent line. It just kind of, yeah, sorry about that. Okay. I don't know if I can get, I can't get it out of there. Okay. All right, got that? Concavity. Now, look at that point right there. Do you see that point? Do y'all see this is a point where we switch from being concave down to what? Concave up, right? This is a change in concavity. Anytime you have a change in concavity, that is called an inflection point. And that is where your second derivative will be 0. Remember the first derivative being 0 meant where we might have, first derivative 0 is where we have flat tangent lines. Second derivative equal to 0 is where we have changes in concavity. You're either going from a frown to a smile, or, do you see a second inflection point? Right there. There we're going from a smile to a frown, right? And then we'll have a third one. All right. Now, this is a very kind of childish way to describe what concavity is, right? I mean, smiles and frowns. So I want to at least show you what concavity means mathematically. Mathematically, concavity is this. Notice if I bring that tangent line in, where is it? Oh, there we go. If I bring that tangent line in, I want you to notice something about when I'm concave down. Do y'all agree I'm concave down there? Right? Concave down. I'm part of the frown. Notice that the tangent line lies above the curve. Right? That line is above the curve. Do y'all see that? Except for the point where they touch. Otherwise, if you go out here, these points on this graph, on the tangent line, are always above the derivative. Above the graph itself. And that's going to be that way. The tangent line is above the graph until I get to where it switches concavity right there. And now do you see that the tangent line is below the graph? That's what it means to be concave up, when your tangent line's below the graph. And then it's going to switch again. Watch right here. We're going to switch to, now the tangent line is above the graph until I get to down here, and now the tangent line is below. So let me show you the definition. Just, it's not going to say smiles and frowns, okay? It's going to say, if a function f lies above all of its tangent lines on an interval, then it's called concave up. If a function lies below all of its tangent lines on an interval, then it's called concave down. You don't need to worry about that definition. You can just think about smiles and frowns, all right? If the second derivative of a function is positive on some interval, then you are concave up. Concave up is a smile, right? And that's easy to remember, right? Positive second derivative. Positive people like to smile, yes? Negative people like to frown. If your second derivative is negative, you're going to be concave down. It's going to look like a frown. Any point on the curve where you have a change in concavity is called an inflection point. All right, let's do an example. Yes.
By the definition.
Yeah.
And the tangent line is above, it's concave up, right? Is that what you're saying?
No.
No.
If the tangent line is above, then it's, wait a minute. If this is saying if the function is above the tangent lines.
Oh, okay, so if the tangent line is below, it's concave up.
Yeah, so look at, here's a function that if I go to any tangent line, so let me go to this point and draw the tangent line. Do you agree that that function is above the tangent line? And same here, draw a tangent line. Do you agree that the function is above the tangent line? Okay, that's concave up. Now, if you try and draw something where it's the other way around, like this, now the function is below all of its tangent lines, right? And that's what concave down means. All right, let's do, I want to do a more involved problem than we did last class. Something like 5x to the 2/3 minus 2x to the 5/3. Yeah, let's do that one. So here's a function, f of x equals 5x to the 2/3 minus 2x to the 5/3. Here are the instructions for this problem. I'm going to put the instructions on the side because I'm going to try and do as much work on there as I can. The first thing I want us to do is I want us to find where f is going up. That's from last class. Where's the function increasing? Second thing I want to do, I want to find where this function is decreasing. Where is it going down? Next thing I want to do is find any local maxes and mins. Those first three steps are what we did in class last time, right? But now, in addition to that, I'm going to add some more steps. The fourth step, find where this function is concave up. Now, how am I going to say concave up to you? I could write the words concave up, right? When I said increasing, I told you I was going to just draw an arrow, right? When I want you to do concave up, figure out where it's concave up, I'm just going to draw a little smile next to this like this. It's not a smile, just a little, almost looks like a little parabola. That's me telling you I want to know where the function's concave up. What am I going to ask next? Yeah, where is it concave down? Find where f is concave down. And then finally, I'm going to ask for the inflection points. Find any inflection points. All right, let's do it. If you want to think about it in groups, this first section of problems, right, is going to require that we are looking at the first derivative, right? And the second group of questions here is that we look at the second derivative. We're going to need both derivatives to do this, right? But let's just start with the first derivative. I think the first derivative of this function is going to be pretty straightforward, I think. I don't know. How do you take derivative of this? You can do them separately, right? Bring the 2/3 out, bring the 5 to the right, bring the 2/3 out, x to the negative 1/3, and then minus, leave the 2, and then bring the 5/3 out, and then x to the, what's that? 2/3? Y'all know what I'm doing there, right? Just power rule? Do y'all know? Yes, no? Just bringing those numbers, bringing this number out, and then I'm subtracting 1 from that in my head, and then I'm bringing that one out, and I'm subtracting 1 from that in my head. Let's just work with this, all right? Let me clean this up. This is the same as 10 over 3x to the 1/3 minus 10x to the 2/3 over 3. So all I did there was put these numbers together. That was 10/3, and then because of x to the negative 1/3, I dropped it down to the bottom as x to the 1/3, right? And on this one, same thing, 10/3, and then since that was x to the positive 2/3, I left it on top with the 10. Any questions there? I have to clean this up, don't I? Why do I have to clean it up? Because what am I going to do with it?
Is it equal to 0?
I'm going to figure out where it's 0, and I'm going to figure out where it doesn't exist because I'm trying to find the critical numbers, right? So the very first step here was to take derivative. Got it. Okay, derivative's done. Now find the critical numbers. So the critical numbers, to do that, I need to figure out where's that derivative equal to 0. I need to figure out where that derivative doesn't exist. Let me just do this over here. Where's that derivative 0? Where does it not exist? So for my critical numbers, let's do where's the derivative first. Where's the derivative 0 first? All right. I need to set that equal to 0, don't I? All right, what do you think I'm about to do? I'm going to get a common denominator. And I told y'all last class, there's a lot of different ways you could solve this equation. But I'm a big fan of getting a common denominator and then only having to worry about the numerator after you do that. So what am I going to need to do to get a common denominator? Multiply this one here by what? X to the 1/3 on top and bottom. I already have a 3. I have 3 here, x to the 1/3. I had a 3 here. I just need x to the 1/3, top and bottom, right? And that's actually going to be really, really nice because what I get on top there, 10 minus, and these two together is what?
1.
X to the 1, right? Which is just x. So 10 minus 10x over your common denominator, 3x to the 1/3 equals 0. Questions there?
No, because it's 3 over 3.
Because it's 3 over 3. Yeah. When you do these together, you add the exponents, right?
Yeah.
2/3 and 1/3 is 3/3. 3 over 3 is 1. We're good? Sure? So now that a fraction equals 0, I only look at the top. 10 minus 10x equals 0, right? From here to here, I'm just looking at when the top is 0. And that I can solve. I'm going to trust you can solve that. X is 1. A couple of ways you can do that, right? We have one critical number so far. What do you have to check about this critical number? Is it in the domain of the original function? Now, I did not look at the domain in the beginning. And maybe you, as you know, it's your prerogative. You could look at the domain in the very beginning of the problem if you wanted to. Or when you get to this step, you could be like, well, I need to make sure it's in the domain, and just go look at the domain real quick. I've always looked at the domain at this point, all right? Because it is possible that I get no solution here, and then I'm not worried about domain at all. So I need to worry about the domain right now. So let's go back to the original function here. Are there any domain restrictions on that?
No, because it's a polynomial.
Why is it not a problem that I have a fraction up here? What does 2/3 really mean? X to the 2/3. What does it really mean?
2 divided by 3.
X.
X to the cube root.
It's x squared to the, cube root of x squared. That's what that means, right? And the other one is really x, to the 5th cube root? And because these are cube roots, I can have negative numbers in there, right? Yeah, so I would only be concerned here if these were square roots or 4th root or 5th root. Then I would have some domain restrictions, wouldn't I? So I'm not worried about anything plugging in here and giving me like an imaginary number. And then I also don't ever see that I'm going to have a fraction where I'm going to have division by 0, right? Do y'all agree? So the domain of that's everything. There's no restrictions. So if you want to, you can put here, domain of this is all real numbers, everything, right? So this critical number is good because 1 is in that domain. Good, good, yes, no? Yeah, what's next?
Find doesn't exist.
Find where the derivative doesn't exist. And I've had some students ask me about this, like they're a little confused as to what I mean by this. Figuring out where the derivative doesn't exist really comes down to you looking at the derivative, which was right here. This was our derivative, right? Cleaned up, that's our cleaned up derivative right there. Now we did set it equal to 0, but before that, that's the derivative, right? By itself. This is asking for you to look at that derivative and tell me if there's any values of x you can't plug in. Is there a value of x I can't plug in? 0. Do y'all see that? I can't plug 0 into this because I will get division by 0, right? This means cube root. That doesn't bother me at all because cube root, I can have a negative. That's not an issue. But the fact that if I plug 0 into this, I get division by 0 is a problem. So this might be one of the first times that we're actually getting something from this, right? I'm recognized just by looking at that, x can't be 0. Since x can't be 0, 0 is a critical number because it's screwing up my derivative. That number screws up my derivative, makes my derivative not exist. So it's a critical number. And of course, 0 is in the domain of the original function because we already said the domain is everything. Y'all good? Any questions? All right, I have 2 critical numbers, and now what do I do with them?
Try to see if where it goes up and down.
Where it goes up and down, so what am I going to do with those now?
Plug in a number line.
Do a number line, plot them, right? And then pick your
Your numbers.
test points. Yes. Okay, good. So I'm now going to draw a number line. I'm going to plot my 2 critical numbers, and I'm going to put them, of course, in order, right? 0 first, then 1. That creates a partition of the number line into 3 regions. And now I'm going to pick 3 numbers up to me, right? These numbers are completely up to me. And what I'm going to do with those numbers is I'm going to use them to see if my graph's going up and down in these regions. So the first number I'm going to pick is -1 because that's a nice number over here to the left of 0. Unfortunately, I have to pick a number between 0 and 1 now, and there's no nice numbers in there, so maybe a half? 1/2. And then I'd like to put 2 here. How about that? I'm going to test those 3 numbers. Where am I going to test them? What do I mean I'm going to test them? What am I going to do with them? Plug them into the derivative. Why?
Because you're trying to find the derivative, the line.
We want to know if the derivative is positive or negative, because positive derivative means my graph goes up, negative derivative means it goes down, right? So I'm now going to test -1, 1/2, and 2, and as a note here, into the f prime, right? That's what I'm doing. I'm plugging those, testing them. I'm plugging them into the f prime to see what I get. And all I care about is positive or negative. That's all I'm concerned about. I actually don't care if the number comes out to be 10 or 100. If it's positive, it's positive. If it's negative, it's negative. So here we go. My derivative, let me write the derivative down so we can have something to look at. The derivative was, the cleaned up version was 10 minus 10x over 3x to the 3x to the third. That's my derivative. And now let's go ahead and plug in. So let's first start with -1. What's the derivative at -1? Okay, up top, you get 10 minus 10 times -1 over 3 times, look at this. The bottom is, I'm going to look at it as the cube root of -1, right? That's what that really means. The top is 20, isn't it? And the bottom is just, what? The cube root of -1 is -1. So I get -3 on the bottom. 3 times -1. So my answer is negative, isn't it? My answer is negative. So let's draw a conclusion from that. What that means is that to the left of 0, right? To the left of 0, my derivative is less than 0. It's negative. But what does that tell me about the original function? It must be going down, right? That's what it means. To have a negative derivative means you're decreasing. And now I've got to do the same thing for the remaining 2 test points. So now into the derivative, I plug in a half. And that's going to suck a little bit, but okay, 10 minus 10 times a half all over 3 times, oh crap, okay, 1/2 to the 1/3. All right, well, tell me about the top. What's the top?
Positive.
It's positive, right? It's positive 5. We got that half of 10. It's 5. 10 minus 5 is 5. So you get a positive number on top, right? And on the bottom, if you take the cube root of a positive number, you should get a positive number, right? So 3 times the positive number should be positive. So again, I'm not really concerned about what I'm getting. I'm concerned about whether or not it's positive or negative. Any questions there? All right, so that means that in this middle region, my derivative is positive, and that means my original function is going up, right? The derivative is positive, which means the original function is going up. The derivative is negative, means the original function is going down. And now plug in 2, right? If you plug in 2, you can check for yourself, you should get a negative. You should get a negative. I'm not going to show that. Students will ask me usually when we get to this point, like, hey, can I just check the first one and then just assume that it's going to like switch, right? Like if this one's negative, then I know the next one's positive, and the next one's negative, and the answer is no. You have to check each one, all right? Every problem is different. So for this one, it does switch. This one over here, the derivative is negative, which means the original function is going down. And from that information right there, from that information, we should be able to answer the first 3 questions now. We should be able to look at that table, this chart that we made here. We should be able to figure out where it's going up, where it's going down, and any local maxes and mins. So I'm going to start answering these questions. The first one, where's my function going up? All right, well, between where? 0 and 1, right? Between here and here, between these 2 dotted vertical lines, between 0 and 1, my graph goes up. So I'm going to write that in interval notation, 0 to 1. For part 2, where's my graph going down? That's a little more complicated. It's everything to the left of 0, so negative infinity to 0, unioned, and then everything to the right of 1, right? A lot of times what students will do on accident is when they give me those answers, they'll accidentally use one of these test points in their interval instead of using the actual critical number. So just be careful with that. Any questions there? I know where the graph goes up and down. All right, how about local max min? Oh. So how are you telling where the local max and mins are? I'm looking at that chart, and what am I looking for? For maximum, local max, what am I looking for? For maximum, up and then down, right? For minimum, I'm looking down then up. All right, so let's start with max, local max. Okay, for local max, where do we have it? Do we have one? Yes. At where? At x is 1. Careful, I'm asking for max. At x is 1, we have a max, right? We're going up and then down. And so that tells me where it is, but what is the actual maximum? Remember, this is the y value. We have to plug this number into the original, right? The original function to figure out the y value. So if I plug 1 into the original function, well, what's 1 to any power? 1. So these are just 1 to any power, 1 to any power. So this just be 5 minus 2, which is 3. Our local maximum is 3. Where does it happen? It happens at 1. Continuing, local minimum. Do it right here. We have a local minimum at x equals 0, and that one should be pretty easy to plug in, right? If you plug in 0, you get 0. So,
Can you explain one more time why you put it in the original function?
because let's go what's happening at 1, right? You know your graph goes up and down, right, at 1, so you know there's a local max, but what we're saying is, well, how high is that point? How high is the point, the maximum? Just take that number and plug it into the original function, you're just getting the y coordinate of that point. So here's what I know. My graph, as you go from left to right, is coming down, and then at 0, it reaches a lowest value, a y value of 0, it comes back up, it goes up, and it hits a maximum of 3, and then comes back down and keeps going down, right? That's what I know so far. Goes down, then up, then down. Questions? Yes?
That's how we found the local minimum, right?
From this picture, right? Down, then up is a minimum, up, then down is a max. But be careful, these points have to be in the domain of the original function for this to work. All right. We've answered 3 of the questions. 3 more to go, right? And this is the new stuff. Where's this graph concave up? Where's it concave down? Where are any inflection points? And what I told you is that we're going to go through the same procedure we just did, except we're going to be using the second derivative instead of the first derivative. All right? So that means we need a second derivative. So we had the first derivative, didn't we? Let's go find the second one. The first derivative, let me write it down here. The first derivative, when we cleaned it up, was 10 minus 10x, right? Over 3x to the 1/3. Please verify. Was that our derivative cleaned up?
Yes.
Yes? Okay. All right, so I need to take the derivative of that, which means I'm going to have to apply the quotient rule. Right? The quotient rule. You don't have to. You could actually split this up into 2 fractions and do it that way, but I'm going to go with quotient rule. Derivative of top is -10 times the bottom, which is 3x to the 1/3, minus, okay, this is tricky. What's the derivative of the bottom?
1x negative 2/3.
Yes, good. So when you take derivative of this, right, on the bottom, the 1/3 comes out, hits that, becomes a 1, then you subtract 1. So x to the negative 2/3. And then times what?
10 minus 10x.
The top, right? 10 minus 10x, in parentheses, 10 minus 10x. And then all over the bottom squared, 9x to the 2/3. So what I did there is I squared this. Squaring 3 becomes 9. And then I squared x to the 1/3. I squared x to the 1/3, and that means you multiply those two and you get x to the 2/3. Y'all see it?